それでは、続いてのご発表は、東京大学の D さんで、Monte Carlo Simulation of Thin Configuration in Thin Film Ferromagnet with Coarse-graining ということで、どうぞよろしくお願いいたします。
Yeah, thank you for your instruction. I'm Li Feng from the University of Tokyo. My supervisor is Sutherland Nakatsuji. I will introduce my recent progress on Monte Carlo simulation of thin configuration in thin film ferromagnets with coarse-graining algorithm. First, I will introduce my research motivation. There are two main kinds of thermoelectric technique. One is the Seebeck effect, and another one is the anomalous nonce effect. We will focus on the anomalous nonce effect today. If I put a material with large anomalous nonce effect in an environment with heat gradient, and the material is itself magnetized, we are able to observe an anomalous nonce electric field E parallel to the cross product of the magnetization and the temperature gradient. If we make thermoelectric devices based on anomalous nonce effect, we can make use of a simple and flexible structure, its shape gradient, and we can control the direction of electric field easily. This is the structure of thermal flux sensor. If we connected ferromagnetic wires with large anomalous nonce effect in series and put it into an environment with heat current, and the materials is itself magnetized in a proper direction. Thus, the direction of the electric field E will accumulate along the path. Thus, we are able to observe large anomalous nonce voltage between the two ends of the device. To intensify the voltage, we can use three main approaches. The first one is to select materials with large anomalous nonce effect. And then we need to ensure that the direction of the magnetization is perpendicular to the directions of the wire. And finally, we should prolong the length of L. So here we have several requirements for good design of thermopile. The first one, we need to have a simple structure. Then we have a dense arrangement so that we can cover the heat source sufficiently. Then we need to use slim and long shaped for a large total length in limited space. Finally, we need to ensure that there is a large remnant in vertical directions. Thus, the anomalous nonce electric field can accumulate along the structure. And I will simulate thin configuration with Monte Carlo simulation. And however, here comes the main problem about the directions of the magnetization. The upper figure is an ideal alignment of magnetization. Here, the directions of the magnetization is perpendicular to the directions of the wire, so that the generated directions of the electric field is parallel to the directions of the wires, so that we can observe a voltage proportional to the anomalous nonce effect coefficient times heat flow times the length of the wire. However, in real materials, due to the existence of shape anisotropy, the magnetization usually prefers to align parallel to the directions of the wire, so that the generated electric field E is perpendicular to the direction of the wire. As a consequence, we are not able to observe the voltage between the two ends. So we need Monte Carlo simulation for simulating the thin configuration. And a natural thought about a relatively ideal thin configuration is using the fishbone structure. In fishbone structures, it is composed by many parallel rectangles. And in each rectangles, the magnetization under the influence of shape anisotropy is perpendicular to the directions of the extensions. And each rectangles are connected with its neighbors. Thus, we still can observe a voltage proportional to the anomalous nonce effect coefficient times heat flow times the length of the thermoelectric devices. And I will introduce the algorithm I'm using named stochastic cutoff algorithm in the simulation. Let's first observe the Heisenberg mode action. A Hamiltonian is composed of 4 terms. The first 3 ones are exchange interactions, crystalline entropy, and Zeeman energy. And their time complexity is of order of n. Here, n is the number of independent spins in the system. However, when it comes to the dipole-dipole interaction, because dipole-dipole interaction is a long-range interaction, it exists between every 2 spin pair. As a consequence, the time complexity is also the n squared. So when the n becomes large, the time complexity is unbearably long. And after introducing the stochastic cutoff algorithm, the time complexity is reduced to the order n times log n. However, we are still facing a series of challenges in Monte Carlo simulation. If we want to calculate the spin configuration from a molecular level using first the spin principle calculation, because there are large number of molecules in real thin films and its number of order is the same as Avogadro constants. The spins usually exceeds the memory of computer, and the form of interaction is fairly complex. And we should wait large on the color steps until the equilibrium status is reached. So here comes the central problem, how to reduce n. In my simulation, I introduced the Coarse-graining model to solve this problem. And in ferromagnets, we know that under the influence of strong nearest neighbor interactions, the spins are almost parallel to its nearest neighbors. So we can use the Coarse-graining models since all the spins in each grain are almost parallel to each other. So we select a representative of spin from each grain, and after the Coarse-graining, only n over L2 independent spins are left. Here, n is the number of spins in the original system, L is the size of the grain. And from this schema figure, we can know that after the Coarse-graining, the spin configuration is still well approximated. And this is my simulation results in ferromagnets with weak dipole-dipole interactions. Here is the original size is 450 times 450, and it is relatively large for our computer to simulate it directly. If I use the Coarse-graining algorithm with a grain size of 9, the independent spins becomes 50 times 15. And this is a simulation result after the simulated annealing of the coarse-grained system. And in this figure, we can observe the flux closure structure, and it is one of the classical structure we usually observe in real magnets in experiments. So this simulation generates the flux closure structure, and this structure generates no leakage field, and this satisfies the least energy requirements. And I will introduce my simulation results on the spin configuration in fishbone structure. And in real thin film, we know that there are shape and entropy like this. So we can see that if the spins are perpendicular to the long side of the rectangles, the dipole-dipole interaction is high. And when the spins are aligned parallel to the directions of the long side, the dipole-dipole interaction is low. So a spin prefers to align parallel to the long side of the rectangles. And after the Coarse-graining, we can see that the value of the shape and entropy is very accurate. And here is the expected simulation result. If we start from the initial state that every spin forms a 45 degrees angle with the long side, after Monte Carlo steps in low temperature, finally the spins will become parallel to the long side. And this is my simulation result after 2,000 molecular steps. Here we can see that all of the spans are almost parallel to the long side of the rectangles, especially the spans in the center parts. If we connected each rectangles by connectors, and thus the voltage of anomalous non-static effect can be observed. And this is the summary of my algorithm. The coarse-graining simulates two-dimensional ferromagnetic system with dipole-dipole interaction with high accuracy, and it reduces dramatically. And in addition, the Monte-Carlo steps to stable state is much smaller in coarse-graining system. My future plan is to develop coarse-graining algorithm for three-dimensional ferromagnets, and later I will use this three-dimensional coarse-graining algorithm to design shape for thermopiles. And I conducted the results of my simulation at Japan Society of Applied Physics meeting 2020. And the final part is my acknowledgement. I firstly contacted the concept of the parallel numerical computations at the lecture given by Professor Lezisuda. And this lecture covers many basic concepts of parallel computation. And at the end of the course, the final assignment is to program with the Oakbridge-CX system. And this is my first opportunity to get in touch of the Oakbridge system. And then I realized the significance of the parallel simulation. And I applied for the female usage plan. And I think that one of the merit of the Oakbridge systems is that I can always get instant and professional reply from the consulting staff. And this is an example. I once consulted the consultant how to install the Python package in the Oakbridge-CX system, because in the first I encountered a problem that I do not have a permission to do so, just like my own personal computer, because it is a supercomputer system. And the staff replied me kindly, and he provided me several solutions to this problem, and it solved my problem perfect. And I'm very grateful for the kind help from the consulting staff. And I can hardly imagine how I can continue my research without the help of the consulting staff. And there are still, and I think that the Oakbridge system is very it's easy to access because we have high degree of freedom in users node, and there are only talks and process of using Oakbridge-CX. The first one is for the application, and the final one is for the final report. And remote work is enabled by simulating with OB-CX system. And I can solve the straightforward information on the status of simulating jobs. And I think that the university provides us sufficient computational results, and the training time is acceptable. And I also want to express my sincere gratitude to my two supervisors, Professor Natsuji Satoru and Professor Miyashita Seiji. And the speaker is sponsored by Merit Wins program as well. Okay, that's all of my presentation today. Thanks for your attention. And questions or comments?